The first thing we're going to talk about today is independent events versus dependent events. You're going to need to learn the difference between the words independent and dependent. Independent means that one thing doesn't affect the other thing. Like, I roll a die again, I roll a die again. I could roll 6 3 times in a row. I could roll 3 times in a row. What I roll on the first roll does not affect what I roll on the second roll. Dependent events depend on each other. So dependent events, one does affect the other. Say I had 5 marbles in the bag of 5 different colors. If I pull a marble out and give that marble away, how many marbles do I have left in the bag the next time I pull a marble out? I only have 4 marbles, so the colors that I could get are changed by what marble was pulled out the first time. So those events would be dependent. And this formula is just saying that if the events are independent, like rolling a die and tossing a coin, those two events don't affect each other. The probability of both of them happening is the probability of the first one times the probability of the second one. That's exactly what we did yesterday. The word and means multiply. Number 1, the sample space for a student randomly guessing the answers to 4 true-false questions is shown below. First of all, if I asked you what's the probability of guessing question 1 and guessing question 2 correctly? Does your guess on question 1 affect your guess on question 2? No. So these would be independent events. Now, we all know that psychologically, if you guess true on the first one, you're more likely to guess false on the next one because you don't want to have too many trues. So it kind of does, but theoretically, your guess on the first question shouldn't affect your guess on the second question. Find the probability that we guess number 1 and number 2 correctly. The way that we did this yesterday, here's the sample space. We want number 1 and number 2. We want the first 2 letters to be C's for correct. In this outcome, we guess correct, correct, incorrect, incorrect. So question 1 was correct, question 2 was correct, the next 2 were incorrect. Are there any others in that row that have correct for the first 2? Nope. Here's one that has the first 2 correct. Here's another one that has the first 2 correct. And there. There are 4 out of 16 possible outcomes where we guess question 1 and question 2 correct. Here's the new way to do that same thing without having to have the sample space to look at. For question 1, I need this question to be correct. How many ways can I get question 1 correct? 1 way out of 2 possible answers. My answers are true or false, so there's 1 correct answer out of 2 possible answers. Question 2, I want it to be correct. There's 1 way for it to be correct out of 2 possible answers. We have to consider guessing on question 3 and guessing on question 4. Question 3, in this particular example, do we care if question 3 is correct or incorrect? We don't care, so 2 out of 2. We could guess correct, we could guess incorrect, both of them would be fine. Same thing with question 4. These are all independent events, so we can multiply them together. On the top, 1 times 1 times 2 times 2 is 4. On the bottom, 2 times 2 times 2 times 2 is 16. Notice we got 4/16, just like we did by counting in the sample space. So this is just supposed to show you that whether you count outcomes in the sample space over the total number of outcomes, or whether you figure it out using multiplication, you will get the same answer either way. Number 2 and 3 are asking you to practice determining if it's independent or dependent. A teacher randomly selects one student to be a speaker and a different student to be the recorder. Are those events independent or dependent? Dependent. Okay, if I select Travis as the speaker, can I select him as the recorder? No. So that would be different than if I selected Shelby to be the speaker, because then Travis could be the recorder. So your first selection limits your choices on your second selection. They depend on each other. They are dependent events. If I have 6 color cubes in a bag, a student randomly selects one cube, replaces it, and then randomly selects a second cube. The first time they select, there's 6 color cubes in the bag. They put it back. The second time they pick, there are still 6 in the bag. Independent. A student randomly selects one cube, does not replace it, then randomly selects a second cube. That one would be dependent. Because if there's 6 color cubes in the bag, you pick one out, you don't put it back, now there's only 5 in the bag. Whatever you pulled out on the first pick will affect what your options are for the second pick. All right, we've got a spinner with numbers 1 through 8. Find the probability of spinning a 5. That would be 1 out of 8. The probability that we spin a number greater than 3, that would be any of these. That is 5 out of 8. Find the probability that we spin a 5, then spin a number greater than 3. This is a spinner. It's independent. The word and means multiply. 1/8 times 5/8 would be 5/64. And then you'd want to write that as a decimal and then as a fraction. Or, sorry, as a decimal and then as a percent. Okay, thumbs up, thumbs down. How do you feel about this multiplying probabilities thing? Basically the same as what we did yesterday because I taught you the shortcut yesterday. So let's skip to number 6 on the back. A bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, and then randomly draw another bill from the bag. We want to find the probability that we are going to end up pulling 2 $100 bills out of this bag. So, the first bill that we draw out of the bag, how many $100 bills are in there? 5 out of how many total bills are in there? 25. Okay, now we take that bill out of the bag and we set it aside. So the next time that we pull something out of the bag, how many total bills are there going to be? There's going to be 24, and then we have to also reduce the number on the top to 4. Now, we might get a $100 bill, we might get a $1 bill, but there is the potential for only 4 $100 bills to remain, so we have to consider that. Basically, think of probability as like, do the numbers as if you're getting what you're trying to get. So we're assuming that one of the $100 bills is no longer in there, so now there's only 4 left. And then you would multiply this together and get 20 over 600. And then we'd do that calculation, 20 divided by 600.
What's up, guys? We're still more back with the video. I can be your intro guy.
Please ignore the disruptive student in the side of my classroom. The first year that I started teaching, I did probability problems with a standard 52 card deck. And I just kind of assumed that all of my students knew what a 52 card deck looked like. And I found out very quickly that that's actually not true. So let's do a quick intro about what is in a standard 52 card deck. A standard 52 card deck is made up of 4 suits. Those suits are spades, hearts, diamonds, and clubs. On your notes, you can't see the colors, so if you are not super familiar with the 52 card deck, you may want to note that hearts and diamonds are red cards, spades and clubs are black cards. So half of the deck is red, half of the deck is black. Within each suit, there are number cards, ace, which is a 1, through 10. Jack, queen, king are called face cards. So these 12 cards are called the face cards. If you actually look at these cards, they have like people on them, so there's a face visible on the card. That's why they're called face cards. We are going to randomly select 3 cards from a standard 52 card deck and find the probability of each event. We want to find the probability that we pick out 3 hearts when we replace each card before drawing the next. So there are 13 hearts in the deck, 13 out of 52. That's the first card that we draw. We replace that card. The second time we draw, there are 13 out of 52 hearts. And the third time, there are 13 out of 52 hearts. So in our calculators, we would multiply that all out. 13 times 13 times 13 is 2,197. 52 multiplied by itself 3 times is 140,608. We could reduce that fraction, or we could just get it as a decimal and then write it as a percent. So it's 0.016. When I have single digit percents, I like to use a decimal, so this is 1.6%. Next, we're going to look at how this is different if we do not replace each card. So our first draw, we have 13 hearts out of 52 total cards. We're not going to replace it. So what should the next fraction look like? 12 over 51. We've pulled a card out, so there's only 51 cards in the deck, and we're going to assume that one of the hearts is now gone, because it could be. So now there's only 12 out of 51. And the third card that we draw, we have to reduce it again, so 11 out of 50. Multiply straight across. 13 times 12 times 11 is 1,716. And on the bottom, 132,600. So that is 1.3% probability. Notice with replacement, your probability is a little bit higher. Without replacement, your probability is lower.